To get back to doing these videos once a week, at least last week. I probably had the time, but ended up procrastinating too much, mainly because I guess the week before and kind of what I was thinking about doing this week or over the last 2 weeks has been like building up in scale. So the videos were getting longer, and I wanted to kind of downsize to more tackleable or manageable tasks. So for this video, I just wanted to talk about duality, and the duality problem that we will be having a test over on Thursday. So it serves for me kind of as a review of the slides that covered the duality problem, and this will definitely be a lot faster than the slides than the two lectures we had on the duality problem, but I just kind of wanted to cover a summary of the duality problem as it pertains to my uh, intro to optimization class 1, operations 1. So there are two problems. There's the primal, which is the original problem that you were trying to solve, such as the window class problem, in which you're trying to find the maximum number of windows or doors that your factories or whatever problem you can do to make. And then you create the dual as an easier way to solve the primal problem. So sometimes it may be easier to solve this dual problem rather than the primal problem. So if your primal problem is a max, the dual problem will be a min. But if your primal problem is a min, your dual problem will be a max. So it's essentially the opposite. And again, it's sometimes easier to solve the dual problem than the max, which is one of the main reasons to find the dual to begin with. A kind of definition of the dual problem is the minimum of the dual should theoretically, if you are at the y stars or the ideal solution of the dual, should equal the max or the optimal solution of the primal. But if you're not at the primal and it is a feasible solution, the minimum of W will always be greater than the max. So at each optimal solution, they're equal, but at a non-optimal but feasible solution, the dual, assuming the primal is a max, will be greater than the dual. So moving on to the primal and dual relationships. So your max of Z is C transpose X, subject to AX is less than B with X greater than or equal to 0 is the essential definition of the primal problem. But with the dual, the subject to constraints, so the B moves up to the minimum with W equals B transpose Y, subject to, so the A or the constraints in A are now flipped. A transpose Y is greater than or equal to C, and then Y is still greater than or equal to 0. Moving on to, from the primal and dual relationships, we're going to be look at different greater than or less than sign changes. This can be tricky. I still probably need to do a little practice, but moving the primal to the dual, a maximum of a primal transitions to a minimum of a dual if most constraints for a maximum would be less than or equal to, and therefore those are sensible. But if you move a less than or equal to constraint to the dual, it will So the corresponding subject to constraints are linked to the variable constraints at the bottom and not the like variable relationships. So yi would be greater than or equal to 0. And there's an odd bizarre relationship such as if you have an equal to, it will be unconstrained for both the top and the bottom, versus a bizarre if your constraint is greater than or equal to. That's kind of odd for a maximum problem because normally you'd be limiting the amount that something can do. Therefore, that's kind of a bizarre, unexpected sign in a maximized problem. So it would flip to be less than or equal to 0. So your yi input would be less than or equal to. 0 just comes from the, moving back a slide, the B or the C relationship in this. So moving on to the bottom half, which would be this part. If yi is greater than or equal to 0, that kind of makes sense because normally you can't have negative numbers, so it's kind of expected to be greater than or equal to 0. It would move to greater than or equal to for a minimize dual problem because normally you don't have negative numbers. Also, the odd, if something is unrestricted, it would go to equal, and it's kind of bizarre to have something less than or equal to 0, so therefore it would go to a less than or equal to constraint, which is, again, weird for a minimized question because it would go to a less than or equal to constraint. So moving on to complementary slackness. Complementary slackness is essentially a way to relate a found solution for your x stars or y stars and being able to relate that to the corresponding optimal solution of the other problem. So for either due to the setup of the equation above, either all x stars are equal to 0 or the sum of y star a is equal to c, meaning that the constraint is at its limit and it's touching that boundary. So, or at the bottom, yi equals 0, or the x constraint is bound. So xj times aji equals bj. So moving on to the example of the window or glass door problem. So this is the original window or glass door problem in which we're trying to maximize 3 different factories. The corresponding dual problem, using the complementary slackness that we derived from the equation above, you get 5 corresponding, either the left side or the right side is true, but from solving the beginning of the problem, or the primary problem, we're able to get that x1 equals 2 and x star 2 equals 6. So using those definitions, we can solve for y star. So since we know x1 star equals 2, we know that from this y1 star has to equal 0 because x star 1 does not equal 4. Looking at the next one, x star 2 equals 12. That is true. So x star or y star 2 does not have to equal 0. And then looking at the next one, 3x1, which it would be 6, plus 2x2, which would be 12, equals 18. So both these constraints are bound. So y star 3 does not have to equal 0. Moving to the top, x star 1 equals 0, x star 2 equals 0. Both these are false, and we know they are false from the x star 1 equals 2 and x star 2 equals 6. So from that, we can derive that y star 1 plus 3 y star 3 equals 3. We know from the bottom that y star 1 equals 0, and therefore y star 3 has to equal 1. So that comes out. Moving on to the next one, 2y star 3 equals 5 plus 2y star 2. From this, and knowing y star 3 is 1, we can get y star 2 to be 1.5, and it's just kind of simple substitution using the complementary slackness easily lets you relate one solution to another solution, or relates your primal and dual solution to prove that it's either right, assuming both are valid, that lets you relate the two solutions. So other stuff going on this week, supply chain, engineering, warehouse, and distribution. We just had our first test today, and we're continuing to work on a carton location unit and moving on with the project. So operations research 1, we looked at the duality problem. Currently we're doing practice problems and trying to review for a test coming up on Thursday. Operations research 2, we have a homework this week, and we're working on the news vendor problem in class. Hopefully I'll be able to review that in one of these videos soon. Entrepreneurial finance and private equity, we're currently reviewing options, which seems a little bit out of the blue, but is interesting. Then for job recruitment season, I had my first internship interview last week. It went okay. Maybe felt a little bit more like a code monkey job, but for Port City Logistics in Savannah. And then this week, I'm trying to prep for my first case interview, which will be with KPMG this coming Friday. So that should be exciting. But I think that's it. Thanks for listening. Good luck. Hopefully this made a little bit more sense. I could have probably presented the sign changes a little bit better, but I think that's one of the most confusing parts of the duality problem that I personally need more practice on. And yes, have a good one. Bye.